talk is about Lyapunov-based deep learning for safe and reliable autonomy. So deep learning, like as we all know, deep learning is very popular nowadays. It's like everywhere with language processing, computer vision, autonomous driving, large language models, and robotics and controls. Like its applications are like tremendously popular nowadays. So the question is, why should we still like particularly use deep learning for autonomy? So there are like many reasons. One of them being deep neural networks have the representation power to be able to map complex higher dimensional nonlinear mappings. It also eliminates the need for handcrafted features. The approach is scalable for like large data sets. Importantly, deep neural networks have the universal function approximation property, meaning deep neural networks can model any continuous function on a compact set. And as a result of this, deep neural networks have become popular for applications across various control systems in areas involving robotics and manufacturing, aerospace, energy systems, smart grids, biomedical applications, and transportation. But despite the increasing popularity, there are still many safety and reliability concerns. And to speak about my main concern, which is more epistemological, I will narrate a story about the clever Hans. Like it was a horse in 19th century in Germany, and the interesting thing about this horse was it was thought to be capable of being able to do arithmetic, and this phenomena actually puzzled many prominent psychologists of that time. In fact, it took one of the famous psychologists there for Oscar films. It took him 3 years to figure out this horse was not capable of doing arithmetic. He was only capturing some subtle nonverbal cues of people around him, like especially his trainer, and but it appeared like he was capable of doing arithmetic. So that begs the questions, like, are models actually learning phenomena, or they could also be learning spurious correlations? And a large part of that is due to like the black box nature of deep neural networks. They lack the interpretability, and they lack certification. They are also very dependent on data. That means their performance can degrade on unseen scenarios. They are also brittle. They're not robust to adversarial perturbations, although like there has been some good research trying to address that. And but most importantly, they don't have analytical guarantees like safety, which is very important for control applications. So the question is, how do we move from the empirical success to theoretical guarantees? So I have made this figure to illustrate how the fields of control theory in general and deep learning have evolved over time. And we can start with the history of control theory from 1920s or so. Like the PID controllers came around that time, and then you can see like these blue dots represent how some milestones in control theory. And for deep learning, the idea of neural networks in general start from the perceptron model, which came in 1957. But for the next 30 years, there was not much progress in this area. There was a period called the AI winter, where some machine learning theorists thought it would not be appropriate to proceed with this idea. But one breakthrough came around in 1986, like when backpropagation approach became popular, and I think that was also a period when we saw a growth in more compute. And in the 1990s, we see neural network-based controllers, they start appearing. However, most of these results were focused on shallow neural networks, but more recently, deep neural networks have become popular, like especially with the growth of deep learning in like around like 2006 or so, and now there have been like many other progress. But my specific area of research, which is Lyapunov-based deep learning, this is what I'll be talking about. So to give a clear idea of what I'm talking about, like consider this simple control affine nonlinear dynamical system. I am omitting the control effectiveness term here for ease of illustration. But so let's say f of x is an unknown drift vector field which is being approximated using a deep neural network. And our control objective is to ensure that we track bounded reference trajectory xd of t, which lies on a known compact set. Since f of x is unknown, the idea that we're going to explore here is we can model f of x using a deep neural network. We can leverage the universal function approximation property of deep neural networks to be able to model this. So there are two approaches to do that. A popular one is using offline training. That means you could collect batches of data based on prior experiments. Like you can collect trajectories from prior experiments, and you can create data sets, and you can do batch training, and you get a static model. And that is the most popular paradigm, but it has its own drawbacks. Like one of them being it involves state derivative information, although that's not like the major issue here. The major issue is like it is not able to adapt to changes in the dynamics, or like changes in the environments. Like there could be like real-time disturbances or so. So a static model is has these limitations, and the approach that I talk about here is of real-time adaptations, where we can update the weights of this deep neural network in real time, and which gives you a dynamic model, in the sense the weights are changing in real time. But if we are updating the weights in real time and also implementing that as a closed loop approach in the control input, then we have to ensure that the control and adaptation, these loops, result in a closed loop dynamical system. So that also means that the update laws that you designed for such a system, they have to guarantee stability of the entire closed loop system. So what I explore here is a Lyapunov-derived approach, where the update laws are derived from the following Lyapunov-based analysis if we substitute the update law that we derive. So when I say Lyapunov-based deep learning, there are like a lot of confusions, typical confusion that show up. So that's why I made this diagram to be clear about what I'm doing and what I am not doing. So like I said, I'm not doing standard offline deep learning. I'm not minimizing a loss function, and it's not doing a gradient descent or back propagation on a static loss function. So that's not what I'm doing. I'm also not implementing the Lyapunov function like a CLF, and I'm not using the Lyapunov condition as a constraint on the control input. No, that's also not what I'm doing. What I'm doing is a constructive Lyapunov-based design. So I start with a Lyapunov candidate and then do an algebraic derivation there, and that gives you this V dot condition, and from there I derive the control and adaptation laws to ensure closed loop stability. So basically adaptive control, but for deep neural network parameters. Now you might ask what's challenging about doing adaptive control for deep neural network. Sorry?
Could I quickly interrupt you here? When you said algebraic relation force dvdt less than 0, do you know the vector field, or at least the drift vector field in this particular context, or that's unknown? Because in one of your previous slides, it seemed to me that you said F, which is the drift vector field, is kind of unknown.
Yeah, it's unknown. So I think it would be easier to. Well, I should probably just answer it here. So F is unknown, so that is a challenge. But we use the universal function approximation property. So we substitute f of x with some unknown. Like a deep neural network representation with an unknown parameter theta star, and then we construct an adaptive estimate theta hat, and then we talk about convergence, like theta hat converging. Yeah.
Right. So which one is the is the deep neural network? Is it V or is it the F? Which one are you?
No, F is being approximated using a neural network.
Approximated by a neural network, and V is being what, derived, or is this? This Lyapunov candidate V, is that also a neural network or no?
No. Okay. The Lyapunov function is pre-selected. Like usually we just select. I think it would be clear in the next slides.
Sure. Please go ahead.
Yeah. Okay. So that's the approach that I talk about, and let me talk about. Let me give more context about the problem that I address. So there were initial approaches. There is like a famous classical approach from like 1996. This was a classic paper from Frank Lewis on multi-layer neural network robot controllers. So there he developed this adaptive estimate of f of x, and here he used a shallow neural network. So W hat transpose sigma, which is activation function, and B hat transpose x, and this gives an adaptive estimate. So there are like there are ideal weights, W star and V star, and then he develops real-time estimates, W hat and V hat. So this gives this F hat estimated term, and then he substitutes that into the closed loop error system and goes like a few steps forward, and then he picks this. This is the Lyapunov function that he picks. So this is like based on the filter tracking error term, and then there are like two other terms representing the weight estimation errors, and those go into the Lyapunov candidate, and from there, like from the following Lyapunov-based stability analysis, he derives these weight update laws. So these are the weight update laws that he derived for the neural network based on a Lyapunov-based stability analysis. So yeah, that was a very interesting approach, and but the question was like, okay, this derivation works for a single hidden layer network. But the question is, how do we extend this development for arbitrary neural networks? Neural networks with an arbitrary depth, for instance. So this is a constructive process that has to be followed, and it remained an open question. There was no general answer. So let me talk about other works that try to address this gap. I mean, they do address that to an extent, but in a different way. Another popular approach is to do offline training for the inner layer weights and do online updates for only the output layer weights, and that is much easier to do because the output layer weights are linear in parameter, and when you have a linear in parameter system, then it is easy to do standard adaptive control approach. But then the question is, how do we still update the inner layer weight? So that remained an open question. But although the contribution in these prior works was they developed domain shift invariant representation for the inner layers, meaning with this domain shift invariant approach, like they use meta learning based approach, where with that approach they are able to show robustness even with like time varying wind profiles, and they did this experiment in a wind tunnel at Caltech, but doing real-time inner layer weight updates still remained an open question, which I address in my 2022 work published in Control Systems letters. So just briefly to summarize what I do, there is this deep neural network architecture. So there are like k number of layers. So this is a fully connected DNN architecture, and based on that, develop this control and adaptation law. So this is a control input, and like the first 4 terms that show up are like fairly standard in like a constructive nonlinear control. But this last term here is the deep neural network based term with a theta hat estimate, and the theta hat estimate here updates using this projection based adaptation law, where gamma is the learning rate matrix, and this term here represents the Jacobian of the deep neural network, and E is the tracking error. And then picking this candidate Lyapunov function, you can do like stability analysis to show that the tracking error converges to 0. Now the interesting part here is how the Jacobian here works. So derive this expression for the Jacobian, and when you substitute that back in, that gives you this adaptation law. So when we extended this approach from a classical Frank Lewis paper, so it turned out like after doing some like a lot of algebraic manipulations and following a recursive constructive process for deriving the update laws. So we do like some vectorization and Kronecker product operations, and going like many steps forward, it turned out we get this nice representation which looks familiar to an approach which is similar to a linear in parameter adaptive control. But here we have the Jacobian term showing up. So I think that was interesting. But the analysis, when you get to the analysis, there are like a lot more complications that show up, because the Frank Lewis paper had used a Taylor series approximation to address the higher order terms that show up. So he used bounds on the higher order terms when you use Taylor series approximation, and deriving similar bounds for deep neural networks, that gets challenging, and that is where my contribution came. Like the analysis, making sure the analysis works, and the approach is derived from the constructive analysis. So that was the main bottleneck that I addressed. So moving forward from the fully connected DNN, I also explore the ResNet architecture. And the reason to explore ResNet architecture is the fully connected approach has vanishing gradient issue. And the reason why that happens is when you look at this Jacobian term, like if you initialize with small weights, this term might actually end up being very small. The reason for that is if you look at this multiplicative relationships here, small initialization usually gives small initial Jacobians, and that would give a small value for initial theta hat dot. And if you start with a small initial theta hat dot, it usually remains very small, and that is not desirable. But ResNets are able to address that. And the reason why that works is ResNets have this thing called shortcut connections across layers. And when you do a shortcut connection, if you take its Jacobian, you get a bunch of identity terms in the Jacobian expression in addition to the weights that show up here. And what these identity matrix terms do is, even if your initial weights are zero, like near zero, even in that case, you don't have the Jacobian of the ResNet vanishing. And I think that's the key benefit of using a ResNet-based approach. And we did experiments with the ResNet architecture here at the Autonomy Park. So let me just play this video. So there was this quad rotor, and it was supposed to track this figure of 8. And we did comparisons with multiple baselines. So shallow neural network-based controller, and there's a proportional derivative controller, and deep neural, like a fully connected deep neural network, and also residual neural network. And it was a windy environment at this Autonomy Park, and there's also non-linearities coming from the downwash when the drone is like flying near the ground, and there's like ground interaction forces, those effects showing up. And as you can see from here, the ResNet is almost perfectly able to track the figure of 8, but the other baselines, they perform not as well. So that was a ResNet, like fully feed-forward architecture so far. But an interesting thing to explore then was what about memory, like neural networks with memory, like having memory in the architecture encoded, that would allow the network to be able to retain memory effects, like long-term time dependencies. But the difficulty with traditional recurrent neural networks is they don't have the ability to retain long short-term time dependencies. And so researchers had developed the long short-term memory neural network as an approach to be able to better retain the long-term time dependencies and have a better memory capability. But the traditional LSTM architecture, it is developed in discrete time. So when we have to extend this approach and apply that to Lyapunov-based adaptive control, there are like lots of challenges that show up. And I mean, the main thing is that we have to then construct real-time updates for the memory itself. And so to get there, we develop these C dot and H dot dynamics. So LSTMs have the cell state and hidden state. So instead of having discrete time updates for the LSTM states, we construct this inner loop dynamical system. So the LSTM is modeled as a dynamical system here, and it is represented using these equations, and we get the parameter dependencies in these terms, psi c and psi h. And once we are at this point, then we apply a similar approach to derive the Lyapunov-based update laws. There are a few terms that show up in the Lyapunov analysis that can be problematic, and to counter those effects, we use a robust high gain approach. But for the terms that could be canceled using a Lyapunov-based adaptation law, we do derive a Lyapunov-based adaptation law to cancel those terms like that. And then the next thing we explore is physics-informed neural network. So physics-informed machine learning gets the best of the both worlds, like classical modeling approaches versus data-driven approaches. So classical methods are reliable, but they require full model knowledge, and data-driven approaches, they don't need any model knowledge, but we can neural network, and that is something I explore. But the way I do that is it's a non-standard way. So consider an Euler-Lagrange system. So here's the inertia matrix, centripetal Coriolis, gravity, potential effects, and dissipation effects. So the way this approach works is every individual term here is modeled using a deep neural network, and then this retains the relationship. Well, this network is multiplied with the acceleration, and this network is multiplied with q dot, and so on and so forth. And by imposing the structure of these dynamics into the network architecture, we reduce the possible solution space in the neural network representation, and it eliminates implausible or invalid configurations showing up. So this is a better approach compared to like a complete black box approach trying to model the entire network. And the way this works is because M is a matrix and BM is a matrix, so we have to apply, we do like vectorization operations here, and when we do when we go to the Lyapunov-based analysis, when we substitute the dynamics and try to go through the manipulations, we have these terms showing up which involve the dependencies on M and VM. So here again, we apply the property of vectorization and Kronecker product operations, and then it gives us these terms. And when we are at this point, it becomes easier to develop a Lyapunov-derived adaptation law. So the Lyapunov function in this case is not like a single theta tilde parameter, but we have theta tilde for every component showing up. And based on this, we derive these Lyapunov-based adaptation laws. So there is the theta hat dot m vector, this adaptation law showing for the inertia matrix, and this is the adaptation law for the centripetal Coriolis, and so on and so forth. And from here, we can guarantee that E goes to 0, and the filter tracking error R also goes to 0 as T goes to infinity. And yeah, so that was physics-informed learning. But in the slides so far that I have discussed, we still were focused on tracking error convergence. That was the main objective that was being solved. But we usually don't care just about trajectory tracking, that we are able to track a reference trajectory. Like the goal of adaptive control in general, and same thing would apply for like, because I'm talking about learning here. So it is also important whether we have a parameter convergence result. So the topic I explored here is being able to do simultaneous online system ID and control. So being able to achieve parameter convergence as well would be interesting. So to this end, I developed this composite least squares adaptation law involving a prediction error term. And this approach, when I explored this approach, I initially was trying Slotein's classical composite adaptation approach, and was going to try to see if it would directly extend for deep neural networks, especially the inner layers. But there are challenges when I tried doing that. The main challenge especially was like Slotein's classical approach used low pass filters on both sides, but that approach that approach is not directly applicable to deep neural networks for developing the prediction error because of the nested nonlinearity showing up. So if you apply low pass filter on both sides to get rid of the state derivative term for developing a prediction error, it would work for linear in parameter systems, but the low pass filter would not be able to separate the inner layer terms if we tried applying that. So that was the major challenge when trying to apply composite adaptation law there. So to just obviate this requirement completely, I developed this new prediction error formulation, which is based on an observer development. So what I developed is essentially an extended state observer, and that gives you an estimate of f hat. So f hat is a secondary estimate of f based on an high gain observer. So and then f hat works like a ground truth information. And so although you don't know f, you know f hat because it is coming from an observer you designed. So then the prediction error formulation is f hat minus phi, which is the DNN with its theta hat estimate. And based on that, I developed this composite least squares adaptation law, and this is the adaptation gain gamma, which is a time varying gain because it's coming from a least squares approach. So least squares adaptation is supposed to minimize the least squares cost over a time window. So that is what I do. But there is a bounded gain time varying forgetting factor mechanism that I use here. So this is a traditional approach in adaptive control, which I also apply here. But the interesting thing about this mechanism is it is able to show system identification, like parameter convergence to a neighborhood of the origin under the uniform persistence of excitation conditions. And these guarantees are very useful. I mean, being able to guarantee system identification, what does it mean in terms of the outcome? So system ID would allow for using the model for the learned model for intermittent feedback systems and for anomaly detection. And that is the key application of this in this result that I'll talk about soon. But yeah, before I get into that, I'll talk about intermittent feedback. Like what is intermittent feedback? Like intermittent feedback systems are systems that have intermittent loss of feedback, and that could happen due to various reasons. Like one of them could be you could have robots operating in the limited camera field of view. There could be GPS denied regions or like occlusion zones coming from like many sources. So that's an interesting problem to talk about. And so when you have intermittent loss of feedback, like you essentially end up with a switch system. And we know like I don't think I need to like give a switch systems background to like a Syscon audience, but overall the approach here is because switch systems can become unstable even if the every subsystem is stable. We have to be careful with this. But what I do here is I consider the feedback denied mode as an unstable system. So the system itself is treated as an unstable system. So for example, if we lose feedback here, so the red part is when you have loss of feedback. And in that case, you consider like the worst case blow up time and treat it as an unstable system. And then that gives you dwell time conditions. Like as a result of like multiple switchings here, like loss and gain of feedback, you want the overall trajectory, like the Lyapunov function, to be going down here. So that's the idea that we apply. And in the paper, I use I derive these dwell time conditions explicitly. Yeah. So Then I applied the composite adaptation law to an unmanned underwater vehicle here. So you look at this simulation results. So the gray patches are when there was loss of feedback. And as you can see from these plots, look at the brown line. The composite adaptation law, like it was able to identify the system dynamics. Its performance was well in the sense, and there is a loss of feedback. It is still able to uh, predict. It is implemented open loop. The model that is obtained by the composite adaptation law when there is a loss of feedback. And as you can see, the composite approach is still able to keep the tracking errors pretty low despite the loss of feedback. And if you look at the other baselines here, they start blowing up at a higher rate. So that is a key advantage of the composite adaptation law that I developed. So I talked about like tracking and system ID so far, but another important goal in control theory is ensuring constraints, or like state constraints, like being able to give safety certificates, like forward invariance results. So control barrier functions are a powerful tool to achieve that. And CBFs ensure safety by translating constraints on the state to constraints on the control input. And that means that safe control inputs satisfy this inequality. And these usually go as a constrained quadratic program. But the thing with this inequality is it depends on f of x. And you can implement this as a constraint only if f is known. But what if f is unknown, especially in the context that we are talking about, like for uncertain systems? So the philosophy here basically is you could replace f with its estimate f hat. But then if we do this, then we also need to account for the error in the estimates. Otherwise, the approach would be invalid. So if we have f tilde term here, this term is still unknown. So the question is, how do we construct like new constraint to also account for the error in the estimate? So yeah, the good news is we can develop bounds on this. So if we have ways to develop a good bound on f tilde, then the problem is solved. And that is basically what I do. Like there is a bound on f tilde that could be constructed. So there are like two different types of approaches that could be explored here. Like one other area of my work was based on like rise and disturbance observer, that those types of paradigms. And rise-based observer is able to show exponential convergence of the disturbance observer error. And the other approach is obviously deep neural network-based system ID that you could do. There are like pros and cons of both, but the benefit of using a deep neural network best estimator here is you could also extrapolate the model information in the future, like in intermittent state feedback or so. But before I get into that, let me tell about this f tilde term with like I mean this is the bound on.
Omkar, can I ask one? Can I ask a basic question, which it's kind of I was.
Yeah, sure. Go ahead.
Yeah. So, see, if there is some uncertainty in the model, which is what you're referring to, right?
Right.
Then the natural approach for such a problem would be to do reinforcement learning. What you seem to be having in mind is that there is a modeling phase in which the model uncertainty is somehow you try to reduce it and use a neural network to model it, and then
Yeah.
along the way later then having modeled it as a neural network with some bit of error, you then now want to design controllers on top of it. Is this correct? Is this the pipeline you're looking at?
Basically, yes.
Right? Firstly, so my question then is, where is this pipeline more applicable as compared to reinforcement learning, in which one learns the control policy as part of as is a part of the course. I mean, as you control, you learn. You don't care to learn the system really. You just learn to control the policy.
Yeah. I mean, yeah, that's
Learn the control policy. Okay, so where
right.
is your approach more applicable as compared to reinforcement learning?
Yeah, so yeah, that's a really interesting question. So yeah, I think reinforcement learning is like it's also an approach with it just is a completely different type of approach to solve like similar problems. And I agree, it is, but I think these approaches are just different approaches. But although I should also add, like I don't have uh, slides on this. Like I wasn't planning to talk about the reinforcement learning side of my research, but I have applied like some of these works to reinforcement, like one of the reinforcement learning problems, which is approximate dynamic programming. What we do there is online ADP. So yeah, I think that would be like a complete, that would go on a tangent from what I'm talking about. But briefly, we use actor critic networks there, and there we
Sure.
explore
Okay.
real-time adaptive update
Okay.
laws. So
So if I
this is what, sorry.
so Omkar, yeah, there's a follow-up then. In that case, so let's assume this is, for whatever reason, this is the approach we want to take. We want to take some amount of data, model the system, and then design a controller. Okay, if that's so you have some open loop data, you use that to model the system, then you design a controller on top of it, and the model is done using neural networks. Let's take that, suppose that is the approach, and now in this sort of a case, the natural way of looking at the problem would be through robust control, right? So why is that not the approach? Why is that not the lens you are using?
Sorry, what did you say? I didn't like really hear you. Natural approach would be.
Robust control, I said.
Oh yeah. Robust control is like one way to go. Like robust control approaches are like high gain type of scenarios, right? I mean, you could use high gains, but then you could argue that it's a debate on like robust control versus adaptive control in general. Like you could use high gain controllers, but then they consume more energy. Like they are like it involves more control effort. Because you're trying to crush the disturbance based on, or the uncertainty based on the worst case scenario, and compare that to adaptive approach where you try to like estimate and compensate accordingly. So I think uh, that's the difference. And on top of that, like intermittent feedback type of scenarios that I talked about, yeah, I don't think the robust control approach would be able to do that, because when you have like complete loss of feedback, then you cannot really rely on like the state feedback, like the high gains. And that is when you have loss of feedback, you have everything is basically open loop, and then you need a good model to be able to make predictions. So that is a thing. If that answers your question.
Okay, fine. Go ahead.
Yeah, sure.
That
Yeah.
leads to a slightly different question.
Yeah.
In your work, you are modeling the error as something small. Is that correct? You have a baseline model that has a neural network which accounts for deviations from that particular baseline model. And of course, that particular neural network is going to have some errors, and the errors are small, hopefully in the uniform norm. Is that right?
Yeah.
So robust control deals with small errors.
Yeah.
So why not use the robust control paradigm for your work?
No.
Instead?
Yeah. So So wait, are you talking about like offline network?
You are designing things online. You are actually tuning the weights online. Am I correct?
Yeah. Sure. Yeah.
Yeah.
Right. I mean,
Yes, go on.
yeah. So the approach I have is you could compensate for like a large part of the uncertainty. Like the adaptive approach is compensating for a large part of the uncertainty, and then uh, yeah, by canceling cross terms and so on, or the other way where you are able to like learn and compensate for the dissonance, but there is still some residual error, right? I mean, even like the best neural network architecture cannot like perfectly model. So for those remaining small terms, there is like robust high gain term that I use. Yes, I agree.
Sure, go ahead.
Yeah. Okay. Yeah. And I can take more questions. I just have like few more slides, and then
Yeah,
yeah.
Omkar, yeah, I was going to request, can you finish with your slides in the next 2-3 minutes and then maybe
Yeah.
few
Sure.
questions?
You're right.
Yeah.
So okay. So yeah, talking about safety and intermediate feedback. So similarly, like to like the talk about Lyapunov functions, like we can also have like safety under intermittent state feedback, but yeah, we have to derive dwell time conditions in an analogous way. But you can make open loop estimates based on similar approach that I talked about earlier. And then when you have loss of feedback, then this is the quadratic program that you have to solve. And we also did a simulation study for that intermittent feedback, safety under intermittent feedback. And there is this, you can look at this plot where X here marks the time instances where feedback was lost, and here the feedback was regained. And compare the baseline with you compare with the baseline, which is based on disturbance observer. And as you can see here, the baseline method actually violates safety condition. Like if this were like the red thing here is a wall, so it would crash right into the wall. But the developed method is able to ensure safety, like still obeys the constraint despite loss of feedback. And so another interesting thing about control behavior functions is it could be like extended to like a signal temporal logic. So there's like a famous paper, recent like 2020 paper by Lars Lindemann. He showed like how signal temporal logic tasks, like complex tasks represented using STL formulas, can be represented using time varying control variable functions. So the advantage of that is, for example, if you have a signal temporal logic task specifying a requirement like this, you could translate the task, basically write it in terms of a single time varying control barrier function. He gives the procedure for that. And the thing is, in his approach, he still had the issue that F was unknown. So what if F is unknown? What do we do? And we can apply the deep neural network in pretty much the same manner. And we also extended this to signal temporal logic tasks. So this is like 5 robots doing collaborating on a specific task given by like this complex STL requirement. And it is able, with this approach, we are still able to show that the STL task is satisfied despite the uncertainty. And so let me talk about future research plans in a minute. So one of the future research plans that I thought about recently was, you could use foundation models to like complete this loop. So I talked about temporal logic, like which is already able to integrate well within my Lyapunov-based deep learning approach. And now you could use foundation models to specify the STL tasks based on vision language models. And if we close the loop, it gives you a nice pipeline for adaptive embodied AI. And another topic that I'm interested in is like symbolic discovery of control methods. So to give you like a brief background, like recently physicists have been able to discover new laws of physics, or like replicate existing laws of physics just based on data. So those are like symbolic learning approaches that are very popular, and there are like names like AI Feynman, AI Aristotle. You can look at these papers. And one of the common methods to do that is distilling a black box model into a symbolic model. And that's a very interesting area of research. And what I'm interested in exploring is, can this approach be taken further to discover new control laws? And what would be interesting for me is, like, for example, if AI is able to rediscover a method like backstepping, which needed like clever insight. So that would be really interesting. And then the next step would be like being able to discover new control methods, like AI acting as a co-theorist. So that's an interesting idea. And another research plan that I'm interested in is compositionality in dynamics and control. So especially like using category theoretic methods for dynamics and control. So category theory gives you a high-level mathematical language for describing various types of systems. Like you could have dynamics, feedback, and learning across various domains. So you get abstractions and compositionality. That's the key benefit of using category theory in modeling and control. And to give like a basic intuition, like you can think about an end-link pendulum. You know the dynamics of a single pendulum. That's straightforward. Now the next question is, can you like compose n different pendulums to can you do like compositions of them to get like the combined dynamics? So those approaches have been explored recently using category theoretic lenses, but they haven't analyzed control problems in the applied category theory community. So that is a problem that I am interested in. It is called open energy driven systems. And I'll talk briefly about teaching, like my teaching philosophy. So one of the recent points of discussion is like responsible use of AI and LLM. So I'm not like against using AI in general. I mean, students should understand like the fundamentals, so that is important. So for that part, you do need like classroom and like classroom exam and things, or like you could use Viva and so. But I also want to integrate AI in the teaching methodology, and want to teach students to use how to use AI responsibly, because I mean they are going to use that anyways. And another thing is, yeah, I mean I have as a research scientist here and as a postdoc, I mentored many graduate and undergraduate students in my group, so I have the experience to be able to mentor in a similar manner. And another thing about my teaching methodology is the use of interactive open source teaching tools. So you can actually check my website. I have like some open interactive tutorials here. Like these are web-based tutorials, and there's a tutorial on physics-informed neural networks. There is a tutorial on CBFs and SLAM and multi-agent systems. I also explore some of my research topics in those, but they're mainly teaching tutorials as well. So yeah, with that, I'll end my talk. Thanks for inviting me.